Hello my dear friends, very good morning to all. So in the last class we discussed some important facts in the parallel RC circuit as well as RL circuit. So I didn't rub that portion because you have to easily recollect those things. So you have to remember one thing, in parallel RL circuit the admittance was G minus JBL. It can be represented like BC also, right? BC or BL, BC in parallel RL circuit it may be BC, BL. It is in parallel RC circuit it is BC, you may represent like this. So Y will be G plus JBC in case of parallel RC. In parallel RL circuit it will be G minus JBL, G minus JBL, and S is equal to P plus JQC here in parallel RC circuit. But in parallel RL circuit it was what? S is equal to P minus JQL, right? P minus K, this is C, right? This is C and that was P minus JQL or I of T is equal to IR plus J IC of T. There is no change in, because in both the addition of current will give the total current, right? Vectorial addition of current will give the total current. There is no doubt in that or change in that. Or this admittance or power factor concept all we discussed. Now we are going to move a very important session which is nothing but parallel resonance, very very important. Parallel resonance. Okay, so let's see parallel resonance. Let's see parallel resonance. Okay, let's draw a circuit first. This is R, this is L and this is C, and this is IC of T and this is IL of T and this is simply IR and this is V of T and this is simply I of T, I of T. Or we can write like so in a parallel RLC circuit, at certain condition the parallel RLC circuit also shows the property of what? Parallel resonance. So like series RLC circuit, at certain condition it is showed the what? Property of resonance. See, it's called a series resonance. So in similar manner in parallel RLC circuit also, in certain conditions, at certain condition it also exhibit the property of resonance called the parallel resonance. So let's check what is that condition and what happens for voltage as well as current in that condition. Okay, let's see. So I can write like I of T will be equal to what? I of T it will be equal to simply IR plus J into IL of T, right? IL of T plus IC of T. There is no change in that, right? There is no change in that. IR plus J into IL of T or IC of T, right? Correct? So this is the condition for I of T, because the vectorial sum of these will give the value. Simply it will be, you can write like not exactly like IR plus IL of T plus IC of T, and you may find what is IL of T and IC of T, and accordingly you can give minus and plus sign. That is very easy actually. And another thing you may notice that what is here the admittance. I already said to you that whenever you are dealing with parallel circuits, you always go for the help of what? Admittance. Whenever you deal with a series RLC circuit, you always go for the ask for the help of what? Impedance. So admittance will be equal to the admittance offered by this path, let be Y1, plus the admittance offered by this path, that be Y2, plus the admittance offered by this path would be I3. Is it correct? So y is equal to y1 plus y2 plus y3. Let's see what it is. let's see what is this. We already derived that RL circuit and RC circuit. Let's combine together to form the admittance of RLC circuit. So can I write like this: G plus J into BC minus VL. Is it possible? Is it possible to write this? Is it possible to write like this? Because in a parallel RL circuit, we already explained that in a parallel RL circuit, the admittance was G plus J into, in parallel RL circuit it was G minus J into BL. Is it correct? Please check the note. G minus J into BL was the what? Parallel RL circuit admittance. Then parallel RC circuit admittance was, in the previous lecture I explained that it is G plus J into BC, right? So adding together will give the parallel RLC, nothing. Adding together will be the parallel RLC, nothing but. So it will be G, it is corresponding to R, plus BC minus BL will correspond to this also. Simple. Simple. When I multiply this with what? V, that is Vy will be equal to, what is that? Vg plus J into BC minus BL, right? Into V. That will give nothing but Vy is nothing but voltage into admittance. What is that voltage into admittance? Or voltage into admittance means voltage by impedance, right? Voltage by impedance is nothing but current I of t, right? Current I of t. So I of t will be equal to, what is V into G? It is nothing but IR plus J into V into BC. V into BC is nothing but what? IC minus J into V into BL, which is nothing but what? IL of t. That is why I rubbed here, no? Initially I rubbed here. Only by doing this you will find whether it is plus or minus exactly. Okay. So it will be I of t will be equal to IR plus J into IC of t minus IL of t. Another equation, important equation in parallel RLC circuit. Is it clear? Then again I am going to multiply this equation Vy equal to plus again with what? V. What I get? V square y equal to V square G, right? V square G plus J into V square into BC minus BL. Is it correct? Or what is V square by? V square y means V square by Z, right? V square by Z means what? It is nothing but power S. Is it correct? S is equal to V square G means V square by R. V square by R means nothing but the power P plus J into V square BC means QC, right? V square BL means what? QL. It's very important. It's very important. It's very important. So in parallel RLC circuit, you have to remind these three equations all the time. All the time you have to remind these three equations. It's very important. Like series RLC circuit now, you have to remember parallel RLC. For parallel RLC, these equation. There was, you already studied now, series impedance equation you already studied. Voltage equation V is equal to VR plus A into, right now you already studied that. And there was also S is equal to P plus J into QL minus QC was there. But here is S is equal to P plus A into QC minus QL. You have to clearly observe the difference. Okay, you have to clearly observe the difference. And now we are going to the condition for resonance. Condition for resonance. What is the condition for resonance, or how or when it happened? See, in this relation, see in equation number 1, from 1, if BL equal to BC, what happens? If BL equal to VC, what happens? See, in the equation number 1, if BL equal to BC, our admittance Y will become simply G, right? Simply G. Or we can say that Y will be equal to Y minimum. Am I correct? Because mod Y will be equal to, Y is always G plus some term is there. If that term is not there means Y will be of course Y minimum, right? Y will be of course Y minimum, right? Y will be of course Y minimum means there is what? Z max. There is what? Z max. Is it correct? Is it correct? Y is equal to Y minimum means there is of course what? Z is equal to Z max. You can write that also. That means in a parallel RLC circuit, you will feel at a resonant condition. I mean, BL equal to BC is called the resonant condition. So this is called the resonance condition. This is called the resonance condition because at this instant only, what happens, Y will be equal to Y minimum and Z will be maximum. So at this condition, what will be the frequency? Let's check that also. At BL equal to BC means, what is BL equal to BC means? BL equal to BC implies, what is BL? It is nothing but 1 by XL, right? And what is BC? It is nothing but 1 by XC, right? BC is 1 by XC and BL equal to 1 by XL, right? Which means 1 by XL means 1 by L omega. Is it correct? For finding a particular frequency at resonant condition, let be omega 0. So L into omega 0 equal to 1 by XC means nothing but C omega 0, right? 1 by XC. 1 by XC means 1 by C omega 0. The C omega 0 will go upper and it will be C omega 0. Or I can write like, how can I write like 1 by LC is equal to omega 0 square, or I can write like omega 0 is equal to 1 by root LC. Is it correct? So this is the condition for the resonance frequency. Omega 0 equal to 1 by root LC. Or I can write like F0 will be equal to, what is F0? Omega 0 is nothing but 2 pi into F0, right? 2 pi into F0 equal to 1 by root LC. Or I can write like F0 equal to 1 by 2 pi root of LC, right? 1 by 2 pi root of LC. So from this you can find that the resonance frequency is same for both series and parallel connection. Is it correct? There in parallel, series resonance circuit, you may experience that at a resonant condition XL equal to XC was there, right? Here BL equal to BC. Okay, so BL equal to BC or XL equal to XC, the resonance frequency is same, which is nothing but omega 0 equal to 1 by root LC, or in other words F0 equal to 1 by 2 pi root LC. Both are same. Is it clear? So this is the equation for resonant frequency. Okay, and let's try to draw in similar manner. We are trying to draw the two curves regarding see, one curve is that V versus frequency curve, or V of t versus this V of t versus frequency curve. How can we obtain that curve? So this will be the shape of that curve. This is F0 and this is FL, this is FH, and you can say that it's some more height now, and this will be equal to Vm, and this will be equal to Vm by root 2, and this is equal to V of t. So if you draw a graph between V of t or V of t versus frequency, there in series resonance circuit is what I of t versus frequency, but here it is V of t versus frequency. I will tell you what is the reason. V of t versus frequency means, see, this is the shape of the curve. So what is the peculiarity of this point? This peak point, there will be maximum Z, right? There will be maximum Z at resonance. Maximum Z at resonance means the impedance across this V of t will be maximum, so that we will exactly get maximum voltage at these two terminals. See, suppose this is a voltage source, right? This is a voltage source. If this terminal is short circuited, then what will be V here? 0. If this inserted some small resistance here, there will be some voltage, say it be 0.1 volt. If we again increasing the voltage mean we can get the increased value of voltage, right? And maximum value of voltage will be obtained when it is open circuit. Is it correct? Is it correct? The maximum V of t, that this whole V of t will obtain here when it is open circuit. That means the voltage across any terminal is directly proportional to the impedance. The voltage across any two terminals is directly proportional to the impedance. So now in parallel resonant circuit, this point offers maximum impedance. We already know this. We point this. We know this. This is maximum impedance point, or y is equal to minimum. So we can say that at this point there will be maximum voltage, that is nothing but Vm. And similar the case of current, I mean series resonant circuit, there may be what? 3 dB band also. 3 dB band also. 3 dB bands means maximum to 3 dB less. 3 dB less. I will explain what is dB and all in later sessions, because just you know this is nothing but 3 dB frequency. 3 dB, this is minus 3 dB here also, and here also it is 3 dB. 3 dB less, no? Maximum to less 3 dB. So this range of frequency is again called FH minus FL, is again called bandwidth of the circuit. Bandwidth of the circuit. And what is the physical meaning of that bandwidth? In series resonance condition also we experienced a term called bandwidth now. So what is the meaning of bandwidth, or why this region is so much important? This FL and FH region is so much important. Why? Because whenever we transmit a signal, we are always trying to transmit a signal within this FL minus FH region, so that 98% of the signal will be transmitted without loss. That is the significance of this bandwidth. If you send, in 2G spectrum, what scam, 3G spectrum scam, I think you may heard about the term like bandwidth, no? So bandwidth is the region where the 3 dB occurs. That is the maximum. We can't send a signal at this maximum point, no? It is very difficult because it is a single frequency. Whenever we are trying to decrease the frequencies, the signal starts loss. Signal starts losing, because there is a frequency range will happen, no? So whenever we send, see, I will explain one thing, easy thing. Optical fiber, optical fiber. Whenever you send some light in an optical fiber, there is no loss at all, or minute losses will be there. Why? Because it is a single frequency, Light is a source like a structure, a single source like a structure. But whenever we insert two or three lights there, what happen? There may be a chance of interference. So there may be a chance of losses. So like that, whenever we decreasing the frequency range, the losses will be very low. Losses will be very less. But whenever we increasing the frequency range means we have to accommodate some signal into that region, so that more and more frequency will be there, so more and more interference will be there. So there is a chance of what? Lossage of signal. So for avoiding that, what we have normally do is we have to set a signal which is exactly in between this FL and FH, so that 98% of signal can be transmitted without loss. But whenever it is below FL or beyond FH, there may be some band, but signals will be lost. That means the voltage will be short, the voltage will be fallen, for this side the voltage will be fallen. That means we can't produce the signal there. So that is the peculiarity of that FH minus FL, that is the bandwidth of the signal. Is it clear? Okay. So that is a graph of Vm against, or V against the frequency. And let's try another graph which shows. See, I already told you that without revising, it is very, very difficult to understand the concept. Another graph is nothing but Y versus frequency graph. So this is the shape of the curve. FL and FH. Is it clear? Okay. Okay. So can you tell me this region and this region? Whether it is inductive region or whether it is capacitive. Here it is Y, no? Y means 1 by impedance. 1 by impedance. So for lower frequency, in series resonant circuit, for lower frequency, more predominant was capacitance, because whenever frequency is less, we know the capacitive reactance XC is equal to what? We know the capacitive reactance XC is equal to 1 by C omega. So whenever we decreasing the frequency or frequency below certain level, the capacitive effect will be more predominant. But what is Y here? Y is nothing but 1 by XC, no? 1 by XC, no? So the capacity effect will be only there at a higher frequency, not at the lower frequency, because it is 1 by XC, not XC. It will be 1 by XC means simply C omega. So whenever frequency is high, then only it effect will come into play. Play. Like series resonant circuit, whenever the frequency is low, it effect was there in series. But this is the case of parallel. This is the case of series. See the difference? So it is 1 by XC, no? Because we are plotting a graph between Y and a frequency. Y and frequency graph is there. So Y and frequency for Y 1 by XC will be C omega, right? So whenever frequency is high, only capacity effect will come. That means this region is termed as capacitive region and this region is termed as inductive region. See, the thing is very deeper, I know that, but you have to remember all this. This is very, very important. If you know this concept, no, actually the problem regarding this will be very difficult, but that much problem will not be asked because it's lengthy too. But the things you may expect in your examination, like what is FH minus FL, what is the value of voltage and current there, like that you may expect. So that first you have to clear with the theory, then easily you can take the options in your examination. Is it clear? So this will be inductive region and that will be the capacitive region. Is it clear? And this region will be what? Z maximum or Y minimum region. Is it clear? So we can say that at F greater than FH, F greater than FH or F greater than F0 you can write. F greater than F0, the region will be what? The region will be capacitive, right? Capacitive. And at F less than F0, right? F less than F0, the region will be what? Inductive. It is opposite to that series circuit, that you have to keep in mind all the time. Okay. If F is equal to F0, the region will be what? Simply what? Inductive or simply resistive. Simply resistive. Not inductive, simply resistive. Simply resistive. Simply resistive. Is it clear? Is it clear? So this table you have to remind all the time. A question will be asked from that table because that much important table is that. That much important table is that. Is it clear? Is it clear? So we can say that here it is, see, Z will be maximum at a resonance means this series parallel resonance circuit is called a rejector circuit. Rejector circuit. Because in parallel resonance, at the resonant condition Z will be maximum. Z will be maximum means current will be minimum. Current will be minimum. If you draw a graph for current here, you will obtain a curve like this. Because at the Z is equal to maximum means current is equal to minimum. You know this. Because I is equal to V by Z, no? So the current will be, I of t will be very less there. So at that time, the circuit is called a rejector circuit. But in the case of series resonant circuit, at the resonant condition, Z will be minimum, no? Z was minimum there, no? So we can say that Z is only equal to R. So we can say that Z was very minimum there. So we can say that that was an acceptor circuit because current was maximum there. Z is equal to minimum means current was maximum. But here it is not like that. Here it is not like that. Y is equal to Y minimum. I know that. Y is equal to Y minimum. Y minimum means Z maximum because Y is equal to 1 by Z, no? Y is equal to 1 by Z, no? So Y will be equal to Z max. Y minimum will be equal to Z max. That means maximum impedance will be offered by this RLC circuit at a resonant condition. Is it clear? So that this circuit is called a rejector circuit, not the acceptor circuit. Not the acceptor. That important thing you have to note all the time. Is it clear? Is it clear? Okay. Okay. Next we are going to. So up to this it's clear. I think it's very clear to you. There is a term 3 dB. I will explain. Just to know this, maximum to minus 3 dB and minus 3 dB both the sides. 3 dB less and 3 dB less both the side will give the bandwidth. Okay. So it is called a 3 dB bandwidth. Okay. 3 dB bandwidth also it's called. So that's all about this up to this. So let us now discuss. Let's now discuss about what? Q factor. Very important. Q factor in parallel RLC circuit. Q factor in parallel RLC circuit. Q factor in parallel RLC. So likewise, see, in series RLC circuit, what was the equation for Q factor there? Q factor was, it was nothing but VL or VC to R, right? VR, right? VL or VC to VR. Here in same manner, we can say that it is nothing but Q factor is nothing but IL or IC to IR. That is the equation for Q factor. Let's see what it is that. Let's check what is IL by IR. At resonance, okay? At resonance. At resonance, okay? So, what is IL by IR? Let's see that. What is IL here? IL is nothing but this current, no IL. It is nothing but voltage across this divided by impedance of that branch. We can say that IL is nothing but V of t or simply V divided by XL. Is it correct? Is it correct? Or IR is nothing but V by R, right? V by R. So this V and V get cancelled. I will get R by XL, right? R by XL, right? R by XL. Is it correct? Is it correct? Or I can say that which is equal to R by, it is XL here, L omega, right? So at the resonance means it is omega 0. And what was the equation for omega 0 that here? It is R by L into, what is omega 0? 1 by root LC, no? So 1 by root of L into C. 1 by root of L into C. So omega 0 is nothing but 1 by root LC, no? So 1 by root L into C goes outside, I mean top side, right? So it will become, can I write like this, R root L into root C divided by root L into root L. So root L and root L cancel. What I get? What I get? R root of C by L, correct or not? R root of C by L, which is the Q factor. R root of C by L. So did you observe one thing? It is exactly what? Reverse of or reciprocal of what? Series Q factor, right? In series circuit, Q factor was what? Q factor equal to 1 by R root of L by C. Did you remember this? Q factor was 1 by R root of L by C. Take the reciprocal as this. This will give R root of C by L. Nothing. R root of C by L. So please compare those things now. Please compare and study. Then things will be remain all the time in your mind. Things will be remain all the time in your mind. Okay. So that is Q factor, R root of C by L. Similar manner, you can go for this also. You can go for this also. What was that? What was that? IC by IR. You can take IC by IR also. IC by IR also. Whether I get same equation or not, I will check. IC by IR. What is IC here? IC is equal to V by XC, no? V by XC divided by V by R, no? V and V get cancelled. It's simply R by XC, no? R by XC, no? Which is nothing but beta. R divided by XC is 1 by C omega, right? 1 by C omega means C into omega 0, which is nothing but RC into omega 0 is nothing but root of LC, right? So it will become RC divided by root L into root C. This C can be represented like, the same C can be represented like what? Root C into root C. So C and C get cancelled. It will become again R root of C by L. R root of C by L. Same equation you can find there also. Same equation found you can find there also. So it will become IC by IR will be, in both the cases, Q factor will be R root of C by L. It's a very, very important relation. It's very, very important relation. R is equal to, sorry, Q is equal to R root of C by L. Compare it with it all the time, please compare it with the series RLC circuit. Okay. Then things will be very, very easy for you. Okay. And here also, there is a relationship between bandwidth and frequency, and there is a relationship here also. F0 equal to root of Fh into Fl. This is all every time any series and parallel circuit you can apply this equation also. This equation also very, very important. F0 equal to root of Fs into Fl. Okay, and let's discuss a term called bandwidth now. Bandwidth or BW. What is bandwidth now? So there is an equation for bandwidth which is nothing but F0 by Q. Okay, let's check what it is. What is F0 here? 1 divided by 2 pi root of LC. Is it correct or wrong? Is it correct or not? FC, right? And what is Q? Q is equal to, we got the equation R root of C by L. Is it correct or not? Is it correct or not? Let's simplify this. Let's try to simplify this. What I get? 1 by 2 pi root LC into, I can write like root L divided by R root C. Is it correct or not? Is it correct or not, beta? This L and this L will cancel, and one root C is there, another root C is there, so that my bandwidth will become beta 1 by 2 pi R C. Is it correct or not? 1 by 2 pi root C into root C is again C, so it is equal to 1 by 2 pi R C. Very, very important relation. Very, very important relation. So in I think in series resonance circuit it was R divided by 2 pi L, right? R divided by 2 pi L, but here it is 1 by 2 pi RC. So you have to what? Either you have to derive at the examination hall. It is also possible, no? You have the knowledge of F0, you know the symbol Q, you know the knowledge of Q. Then at the examination center also you can derive for this. Otherwise you have to remind this. Anything you may, it's up to you. It's up to your memory, it's up to your convenience that you have to derive at this examination hall, or you may simply remember this thing. I prefer that derivation, no? An examination can, depending upon need, we have to derive values, because remaining all the things will make you confused, but simply derive at the time, because it is a one step process now. If you know F0 1 by 2 pi root LC, if you know Q, it is a reciprocal of the series resonance circuit Q. So definitely you will get the answer, no? Definitely you will get the answer. Is it correct? Is it correct? Circuit theory is really interesting to you or not? Tell me that. Tell me that. Tell me that. Is it easy now? And now if you understand the concept clearly, then it's very, very interesting and easy. You can play with the equation. You can play with the equation. But if you don't know the basics, it is really hardly know. It is very difficult to you. It's very difficult to you. It will be somewhat a headache for you all the time. Okay. So circuit theory is an easy subject actually, but you have to remain all the things and you have to feel the subject and study. I again and again saying the same thing. You have to feel the subject. You have to feel the subject. Okay. Feeling means you have to clearly understand, and please make it to go inside your heart, not to the brain. Make it to allow it to deeper and deeper goes into your heart. Then only the things will be feelful. Is it clear? Okay, so that about the bandwidth. That's all about the bandwidth. And one more thing you have to derive here, which is nothing but in series resonance circuit, it was there voltage across inductor and capacitor at resonance. Now it is a current across inductor and capacitor at resonance. Current across inductor and capacitor at resonance. See, I will explain that also. That is current across inductor and at resonance, right? Resonance, right? Current across inductor and capacitance is nothing but IL or IC, right? IL or IC. Current at inductor or capacitor is nothing but IL or IC. So let's first find what is IL. IL is nothing but V by XL, right? V by XL. And V is nothing but what? I into Z, correct or not? I into Z, Z divided by XL. Or at resonance, what is Z there? At resonance, what is Z there? Resonance Z, what is Z value? What is Z value? I can say that it is simply R. It is simply R. Is it correct? Is it correct? That will be, what is this R by XL? What is this R by XL? We already derived what is R by XL there, right? R by XL is nothing, R by XL is L omega, and you substitute that, you will definitely get that equation for what? Q. So it will be I into Q. So we can say that IL is equal to I into Q. Is it correct? Similarly, what is IC here? IC is nothing but we can say that V by XC at resonance, or V is nothing but I into Z divided by XC, or which is nothing but I into Z is nothing but R again. At resonance Z is equal to R, no? At resonance BC equal to BL, so that Y is equal to only G. Y is equal to G means Z is equal to R, simple. So X is I into R divided by XC. What is this R by XC? It is again Q. So we can say that IC also Q times I. IC also Q times I. Always Q will be very high value, no? Q will be very high value. So we can say that at resonant condition, in parallel resonance circuit at resonant condition, both the current of capacitor as well as inductor will be Q times the input current I of t. Q times the input current I of t. There is a minimum current, we know that there will be minimum current, we know that minimum current will be but amplified like Q times in across L and C. Clear? Minimum current will be multiplied Q times with the what? L and C, across L and C in parallel RLC. In the same case, series RLC circuit, what was that? Voltage will be amplified Q times across L and C, right? Right? Did you remember that? In parallel series RLC circuit, what was that? V L is equal to QV, we learned that. VC is equal to QV, we learned that. Similarly, in series resonance or parallel resonance circuit, IL is equal to QI, IC is equal to QI. So this circuit is called, that is why this circuit is called current amplifier circuit. Current amplifier circuit, because there is a, we know that in resonant condition there will be a small current drawn by this circuit, no? The total current I of t will be very less, because we already see in the curve that at Y minimum Z will be maximum, so that I will be minimum. That minimum current is amplified to Q times across L and Q times across V, that's all. But these two currents are reverse manner. This is flowing this direction, this is opposite direction. That is why this is cancelled together. That's why it's cancelled out. That's why it's cancelled out. Is it clear? Is it clear? So it is called a current amplifier circuit. In the case of series resonant circuit, it was called what? Series resonant circuit is called voltage amplification circuit or acceptor circuit. This is called a current amplification circuit or rejector circuit Is it clear? Is it clear beta? Is it clear? So that's all about the parallel resonant circuit. Let's check my time now. Okay, time is there. So is it clear to you? Okay. Now we will do some problems regarding the series as well as parallel circuit, so that the things will be very, very clear to you, and you can recollect your equations very, very easily, so that it will firmly go to your mind. Okay. So let's do some problems. Let's start with what? Series resonant circuit. Okay. Let's start with series resonant circuit. Okay, write a question. At a resonance, find one Q factor, 2 bandwidth, 3 I, 4 FH, FL and F0. See? So let's start from the question number 1. We have to find the Q factor now. So this is a series RLC circuit. R is given, L is given, C is given, no doubt in there. Simple circuit now. Simple circuit is another way 10 sin t. Okay. So let's take first the Q factor. What is Q factor? In examination you may expect a question like this. Okay. Q factor is nothing but Q is equal to nothing but 1 by R root of L by C, right? L by C. You have to remember at least this one equation. Take the reciprocal of this, you will give the parallel resonant circuit Q factor. Okay. 1 by R root of L by C, right? So it will become, you can directly substitute the value at 1 into 1, so 1 by R root of, what is L here? 2, what is C here? 1 by 4, right? 1 by 4. It will go outside, no? Upside, no? This 1 by 4, no? 1 by 4. So it will become root of root 8. So Q factor will be what? Root 8. Yes. And let's go to question number 2. That is nothing but bandwidth. What was the equation for bandwidth in series RLC circuit? It was nothing but beta R divided by 2 pi L, right? R divided by 2 pi L, right? So it will be directly, you can substitute that value. It is nothing but 1 divided by 2 pi into L. 1 divided by 4 pi. Okay, that is the bandwidth. And what is the next question we have to find? 3 I, right? I. So at a resonance, I will be equal to simply V by R, right? At a resonant condition, XL will be equal to XC, so that I will be equal to simply what? V by R, because Z will be simply equal to what? R at a resonance. So I will be equal to simply V by R. So it will be simply 10 sin t divided by R is nothing but 1. So this is called I. This is I. 10 sin t is the I. And next we have to find FH, FL and F0, right? So let's first find F0 first. F0. What was the equation for F0 in series RLC circuit? Is 1 by 2 pi root LC. There is no change in that, no? It will be 1 by 2 pi root of L is nothing but 2 Henry, is 1 by 4 Henry. So it will become 1 by 2. So it will become 1 by 2 pi root 2. So in the 1 by root 2 pi. So that is the equation for F0. Clear? Is it clear? Okay. And let's find what is the value of FH, FL. Okay. Let's see that first. Okay, let's see that. So for that we have a relationship that FH minus FL is equal to what? Bandwidth. What is the equation for that? 1 by 4 pi. Let be equation number 1. Okay, let be equation number 1. And we have another equation that F0 will be equal to root of FH into FL. Am I right or wrong? Correct. So it will be F0 square is equal to root F simply FH into FL. Is it correct? F0 square, you know the value of F0, right? 1 by root 2 pi. So F0 square will be equal to 1 by 2 pi square, right? 1 by 2 pi square equal to FH into FL. FH into FL. So FH minus FL is equal to 1 by 4 pi and FH into FL equal to what? 1 by 2 pi square. Here see, I can replace this quantity, right? FL with FL is equal to 1 by 2 pi square FH. So this will be FH minus FL will be what? 1 by 2 pi square into FH, right? FH. This FL can be right like this. From this FL will be equal to 1 by 2 pi square into FH. So 1 by 2 pi square into FH will be FL, which is equal to what? 1 by 4 pi. 1 by 4 pi. Is it correct? I am going to multiply the equation with 2 pi square FH both side, right? 2 pi square FH both side. It will become 2 pi square FH into FH minus 1. 2 pi square FH multiplied. So it will be 2 pi square FH into 1 by 4 pi. 1 by 4 pi. Is it correct? So it will become 2 pi square FH square minus 1 minus this 2 and 2 got cancel and 1 pi and 1 pi cancel. It will become equal to pi by 2 FH. Is it correct or wrong? Is it correct or wrong? Or it will become, see what happens. It will become, when I multiply with 2, here this 2 will be there, that is 4 pi square FH square minus 2 will be equal to FH into pi. So it will become 4 pi square FH square minus FH into pi minus 2 equal to 0. Or divide with 4 pi square for all the time, I mean for all the equation, FH square minus FH into pi divided by 4 pi square minus 2 divided by 4 pi square equal to 0. Equal to 0. I know it's slightly difficult, not difficult actually, it's lengthy. I know, but we will do. We will do. If you know the thing, then we don't want to hesitate. No, we don't want to hesitate. And let's check my time. One more thing. Okay, time is there. Time is there. So it will become, see, how can I write like FH square minus this 5 and this 1 pi cancel, no? So I can write like FH square minus FH by 4 pi minus 1 by 2 pi square equal to 0. So this is a quadratic equation of second order, right? So FH will be what? Minus B, that means 1 by 4 pi plus or minus root of B square, 1 by 4 pi square minus 4 into 1 into c is what, plus pi square whole divided by 2. If you solve this equation, okay, this much difficult will be was, there will be directly simple values will be there, this much difficulty will not be asked, okay, which is, I know it is very lengthy, So if you solve this fh, you will definitely get the value of fh, and substitute, okay, let's try that, 1 by 4 pi square, okay, let's try that. Root of 1 by 4 pi square, so it will be, I will take what, okay, you may take in your own way, it will not be simplified, you will take in your own way, you will get definitely fh, and if you substitute this fh into this equation, or we have there is one relation, this fh minus fl equal to 1 by 4h. If you got the value of fh here, you can substitute for fl also, that's very important. Okay, so that's all about this parallel resonant circuit, and some problem, one problem is there, and we will continue with so many problems in the next class onwards. Okay, so until then, bye. Okay, so take care.